In this section of the course, we are going to introduce the idea of artificial neural networks, or ANNs for short. Specifically, we're going to talk about a certain kind of artificial neural network called a feed-forward neural network. This is the most basic kind of neural network, but as you'll see, the concepts involved go quite deep, and they also form the basis for other kinds of neural networks, such as convolutional neural networks and recurrent neural networks. To begin this discussion, let's start with why and how neural networks came to be in the first place. This is something that a lot of teachers skip over, but it's something that I find quite interesting and inspirational. If you think neural networks are a cool new model to help you pick stocks or play Mario Kart, then you are still looking for the small fish. In fact, neural networks are way more interesting than that. As you may have realized, the name artificial neural network means that we are trying to artificially create a neural network in a computer. Okay, so then what's a real neural network, as in a non-artificial neural network? The name neural network derives from neurons, which are the cells in your brain and extend throughout your nervous system. Now, this is probably too obvious for most of you, but let's state it anyway just in case. Your brain is what you use to think. Neurons in your brain are connected to each other and can communicate with each other via electrical and chemical signals. Amazingly, this simple physical and chemical system is what makes you, you. All of your thoughts and aspirations, your emotions, and every action you take throughout the day, it's all driven by your neurons, which in turn are just sending electrical and chemical signals around amongst themselves. Once scientists realized what the brain was doing and what it was responsible for, the next question was almost obvious in hindsight. Can we build a brain? I mean, if the brain is just a network of neurons, and we can simulate neurons in a computer, if we connect a bunch of neurons through a computer simulation, it seems that it might be possible to create some form of intelligence. An artificial intelligence, you might say. So let's take our model of a single neuron, logistic regression. Now let's imagine that we have multiple neurons, all taking in the same inputs, but computing something different. Now let's do it again. Now we have multiple logistic regressions. Now let's imagine that all these neurons are connected to more neurons. So we just repeat the process, pretending that the new layer of neurons are actually inputs to more neurons. That's basically a very tiny model of the brain, neurons connected to neurons. Of course, this is necessarily simplistic. One side is the input and one side is the output. Of course, the actual brain is much more complex. There are many inputs and many outputs. In the middle, wires can crisscross. If we have a later neuron connecting back to an earlier neuron, we call that a recurrent connection. The neural networks we are about to discuss in this section contain no such complexities. Instead, because the input is on one side and the output is on the other side, and we go from input to output in a layer-wise fashion, we call this a feed-forward neural network. In the rest of this lecture, we are going to outline what we will discuss in this section of the course. First, we are going to start out again by discussing the model architecture. As you know, the model we'll be discussing in this section is the feed-forward neural network. The next step, after discussing the model architecture, will be to go back to the geometric picture. If you recall, my motto goes, machine learning is nothing but a geometry problem. So how do neural networks extend the capabilities of a basic linear model in terms of solving this geometry problem? Next, we're going to go more in depth and discuss activation functions. Activation functions are very important in neural networks. They are what make neural networks more expressive than the simple linear models you saw in the previous section. After that, we're going to discuss how to do multi-class classification using neural networks. If you recall, in the previous section, we only discussed binary classification. This works if we only have two classes, dog or cat, fraud or no fraud, purchase or leave the store, and so on. But what if we have more classes? For example, we might be working on a self-driving car that needs to be able to recognize multiple kinds of objects on the road. In this case, binary classification is not good enough, and we need multi-class classification. Next, we'll switch gears from talking about the neural network itself to a new kind of data, images. Deep learning excels on unstructured data such as images, text, and sound. We'll look at how images are represented in a computer so that we can get back to the situation where we can say all data is the same. Finally, we'll look at some notebooks that demonstrate how to do image classification using a neural network for multiple classes. We'll also look at neural networks for regression and see how they can be much more expressive than a simple linear model.